Okay, so in this section, we're going to take a look at, we're going to revisit and give you a reintroduction to acids, bases, and also salts. And we're going to call upon some of the information we learned in the previous section, but also in the previous class, General Chemistry 1. So we're going to start here, we're going to call some info from Chem 1. Where we had a brief introduction to acids and bases. And then we're also going to recall some of the information that we had from the previous chapter, or the previous section, where we looked at equilibrium. So we're going to be applying some of those equilibrium principles. We're going to start applying them in this section, and we're going to continue applying those equilibrium principles to acids and bases in the next section as well. The first thing I'm going to have to take a look at here is to revisit this whole idea of what is an acid and what is a base. And specifically now we're going to focus on the Bronsted A definition. Sometimes it's just abbreviated as Bronsted as opposed to Bronsted-Lowry. Sometimes you'll see BL for Bronsted-Lowry acids and bases. And in this definition, you would have seen at least two different definitions already. You probably have heard about the Arrhenius definition. And we'll take a look at another definition at the end of this section. But for right now, when we look at the Bronsted-Lowry acids and bases, we look at defining each of them relative to the proton. Okay, so a Bronsted-Lowry acid is a species that is able to donate protons. So the proton is just another word for H plus ion, whereas a base is something that does the opposite. It's able to accept one or more protons. Okay, so in other words, a Bronsted acid is a proton donor, a Bronsted base is a proton acceptor. Now, when that process happens, when something donates a proton, or whether it something else needs to either be accepting the proton or donating the proton from. So there's a terminology that we use to identify both members of that pair, and it's called a conjugate acid-base pair. So for example, if we have this acid here, hydrochloric acid, and we put it in some water, so H2O, what can happen is this HCl donates this proton, the H plus. And where does that H plus go? Well, the only place for it to go would be to the other thing present, which is going to be the water. So in this case here, the HCl is acting as the acid, and the H2O is acting as the base. Well, what the HCl becomes after it loses that proton, it becomes a Cl minus, the chloride ion, and we refer to that as the conjugate base of HCl. So we have one conjugate acid-base pair, and then the other two species in that reaction would constitute the other conjugate acid-base pair. So for example, when the H2O accepts that proton, it becomes H3O plus, because we now stuck an H plus onto H2O. So we have an extra hydrogen in addition to now positive charge associated with it. So we call this species then a conjugate acid of H2O. Okay, so we have two conjugate acid-base pairs in this reaction. The ones in green, the HCl and the NCl minus, and we have the H2O, H3O plus. That's a conjugate acid-base pair as well. Right, so like those. So from here, the conjugate acid-base pairs that we have would be HCl, which would be the acid, and Cl minus, which would be its conjugate, which is abbreviated as CONZ. J, conjugate base. And then we also have the H2O, which is acting as the base now. When it gains proton, what does it become? It becomes H3O plus, which is going to be a conjugate acid of H2O. So we can generalize that relationship We can obviously see this in other examples as well, like in the case of ammonia, reacting with water. Here the ammonia is gaining the proton, which becomes H4 plus the ammonium ion, that's the conjugate acid. H2O is acting as an acid, it's donating a proton, it's losing an H plus. It becomes OH minus, which is now a conjugate base. So the way that we can identify members of a conjugate acid base pair is actually really simple. We can say that the conjugate base of an acid, and this is generally now we can apply this to all situations. In the conjugate base of an acid has one fewer protons, whereas the conjugate acid of base one more proton. One more proton. So in other words, the members of a conjugate acid-base pair differ by a single proton. That's how we can identify them. For given a reaction, for example, we can say what they are, or as in this case here, it says what is the conjugate base of HNO3? It's an HNO3. That's nitric acid. Here, the conjugate base of this, if we go back up here, the conjugate base is going to have one fewer H plus. So we take away an H plus from this, we end up with NO3. We take away an H plus from something that's overall neutral, that NO3 has to have a negative charge. All right. Similarly, the conjugate acid, O2 minus, is the oxide ion. Conjugate acid, according to our general rule, will have one more H plus. So we stick an H plus onto there, so we have an OH. Now the charge is going to decrease by one negative, so it becomes one minus because we stuck an H plus onto it. And you can do that with any species. If we're asked to figure out one or the other, we can apply our general principles up here to identify or to write out what the other member of the conjugate acid-base pair is going to be. This is going to be important as we start looking at some of the reactions that the acids and bases are going to undergo. And we'll use the terminology conjugate acid-base pair frequently throughout the remaining sections.